context for this question is a production line in which boxes of soap powder are being filled with the powder. And we can see here the soap powder in the box. The box is coming along in this direction on the conveyor belt here. That's the level there to which the soap powder box is supposed to be filled. And in order to find out whether they are being filled to the right level and no higher, there is a radioactive source on the right hand side, a detector on the left hand side, so the radioactive emissions will travel through this space here, and if there's too much soap powder in the box, it will then reduce the level of radioactivity which is being detected here on the left hand side. And in part C, the engineer designing the system selects the beta source from this table here. So these are the four possibilities that she's identified, and she's going to decide which of these four sources it is. She decides that strontium is the right one, and explain why this is a good choice. And this is with respect to the suitability of the half-life. So we don't need to talk about any other features of those isotopes, simply in terms of the length of the half-life. So really good way of doing this would be to talk about why the other isotopes would be less suitable. Well, you can see here from the information here that there are two of these, the yttrium and the phosphorus, have got relatively short half-lives, and that would make them rather unsuitable. So let's start off by talking about those two sources there. We're not going to use those. We don't think the engineer should use those because in those cases, those half-lives are really quite short. So let's put down the yttrium and the phosphorus have half-lives that are too short. The difficulty with these, of course, is that it means that the source would become weaker relatively quickly, so the machine would have to be repeatedly adjusted, and in due course the isotope would have exhausted its usefulness. So let's put in now they would need to be changed. They have to be replaced relatively frequently, and of course that then makes the cost of the operation greater. So we've eliminated those two there. Now, of course, that leaves us with another possibility, which is the beryllium. Now, again, we need to look at the half-life with this. As you can see, the beryllium has a half-life of 1.5 times 10 to the power 6. So that's 1.5 million years. So that's really the opposite problem. It's got an extremely long half-life. Well, of course, it's highly unlikely that any machine is going to last anything like 1.5 million years. So that's not going to be a good idea either. So let's put down here the beryllium has a half-life that is too long. So we're agreeing that she's disregarded the beryllium because of this. And now let's put down, there are 4 marks available. So let's put down a way of covering this. It would still be very radioactive when the machine, let's find a good way of putting this, when the machine is no longer being used. So the machine, even the machine lasts 50, 100 years, the beryllium is still going to be really active, and it's then going to be a problem for whoever has to dispose of the machine, so that they've still got a very radioactive isotope that's in there.